Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from Deshbandhu College, University of Delhi. Today we are going to discuss about the module Conducting Polymers and Introduction from the paper Functional Materials. So students, main points which will be covered in this module are: first, the theory of conducting conjugated polymers will be discussed. Second, how are polymers made conducting? Third, a few examples of common conducting polymeric materials. Fourth, the common devices which are made using conducting polymers and their bases of operation and challenges. So students, let us start with a brief introduction about this module. Conducting polymers are very important class of materials which have been termed the backbone of a rather contemporary area, and they are termed as organic electronics. Typically, we perceive the polymers to be non-conducting materials which are mostly used as insulators, where one does not want to conduct the electric current. However, with the advent of conducting polymers, typically pi-conjugated polymers and oligomers, which could be made semiconducting, if not metallic, a plethora of research avenues opened up. This started mainly with the discovery reported by Alan Hager, Alan McDermott, and Shirakawa and the co-workers in 1977 that the polymers such as polyacetylenes could be made highly electrically conducting when they are subjected to a redox chemical treatment leading to oxidative doping with iodine. This discovery eventually resulted in the award of 2000 Chemistry Nobel Prize to these three scientists for the discovery and the development of conductive polymers. Whilst the inorganic semiconductors continue being used in many devices, today one can witness the success of conducting polymeric materials in the form of organic light-emitting diodes and displays commercialized by several manufacturers such as Samsung, LG, Sony, etc. Organic solar cells and a variety of organic devices such as sensors, which could soon lead to commercialization. In these series of a few lectures, we will develop the main important aspect of these materials, namely the fundamental principles of these materials, common devices and how can we fabricate, and their principles and applications. Conducting polymers. A typical polymer chains consist of several monomer units whose number can vary from several thousand to millions, such as in polyethylene, polypropylene, etc. In such polymers, valence electrons are sp3 hybridized, leading to a covalent bonding between the monomers. These electrons possess very little electrical mobility and hence render the materials to be electrically non-conducting or insulating. In contrast, the conducting polymers are conjugated materials where the backbone of polymer chain consists of sp2 hybridized carbon atoms, leading to the formation of three strong sigma bonds, which can be seen in the figure. For example, in polyacetylene, each carbon is bonded to one hydrogen atom and two neighboring carbon atoms. The one valence electron left over occupied the pz orbital orthogonal to the signal bonds and is called as pi electron. These pz orbitals consisting of pi electrons associated with each carbon atom in the monomer unit overlap with each other in the polymer chain, forming a bond known as pi bond, which is shown in the figure below. At times, these orbitals are also called as delocalized orbitals because half-filled nature. The electrons residing in these delocalized orbitals may end up having higher electrical mobility, particularly when the material is doped. The doping, for example, via oxidation or chemical redox reaction, removes some of the delocalized electrons and makes energy states available for the conduction across the array of delocalized pz orbitals. The process is shown schematically in the below figure. Typically, most of the polymers are p-type as a result of oxidative doping. The process is quite similar to what is seen in inorganic semiconductors, example silicon, which is doped with impurities like phosphorus or boron to impart the n-type or p-type semiconducting behavior. Now students, the materials which we are going to discuss in this module are most of those polymers are the ones whose main polymer backbone or chain consists of aromatic cycles or are double bonded. So the first one is polyfluorenes, polyphenylenes, polynaphthalenes and polypyrenes without any heteroatom. Second, polypyrols, polycarbazoles and polyindols, polyazepines and polyaniline having or containing the nitrogen. Third is polythiophene and poly,3,4-ethylene dioxythiophene, or we say it as PE dot, which contains sulfur. Now these are the few materials whose schematic is shown in the figure, which is depicting
their chemical structure. Among these, polyaniline or pani, PPV, and polythiophene have very well researched materials due to their suitability for applications. For example, PPV, polythiophene, and their derivatives have been extensively studied for organic cell devices as they have quite appropriate light absorption characteristics along with the semiconducting nature. On the other hand, polyaniline or pani has been well studied due to its higher conductivity and is suitable for the devices such as electrode material, packaging industry, automotive industry, etc. Materials characteristics. This table lists some important conducting conjugated polymeric materials along with their electrical conductivity values. As the list suggests that dopants have huge potential to tailor the conductivity of these polymers, which can be as high as 10 to the power 5 to 10 to the power 6 ohm inverse centimeter inverse. In the above sections or the following sections, we will discuss some of these polymers from the perspective of their chemical characteristics as well as their synthesis methods and the challenges associated with them. Few examples of these common materials will be discussed in this module.
Now, let us discuss the conduction mechanism or the mechanism behind the conduction of these conductive polymers. In a typical crystalline, semiconducting and insulating materials, the periodic arrangement of atoms and atomic interactions leads to the formation of an electronic band structure. This band structure consists of many energy levels, which basically shows two distinct regions. First is the region of filled state called as valence band, and second is the region of unfilled states called as conduction band. These two regions are separated by an energy gap known as forbidden energy gap. The magnitude of energy band gap, or we can say EG, determines the nature of the material, whether it is semiconducting or whether it is insulator. Most conjugated conducting polymers are semi-crystalline in nature, and interactions between the polymer unit cells again leads to a similar kind of scenario, leading to the formation of a band structure with an energy gap. So by and large, most of the polymers shows the energy gap to be more than 1.5 electron volt, and hence they are poor semiconductors or insulators. As shown by Chang et al., similar to inorganic semiconductors, doping leads to a significant improvement in the conductivity of the polymers, such as in the case of polyacetylenes. While conventionally it was thought that the improvement in the conductivity of the polymers upon the doping due to the formation of partially filled states in the energy bands in a similar fashion as it happens in the inorganic semiconductor. The findings of large conductivity in polymeric materials such as polyacetylenes and polypyrols challenged this hypothesis. It was suggested that it was not unpaired electrons which causes the conductivity, but rather it was caused by the charge carriers which were spinless. The charge carriers in these polymers are not free electrons or holes, as is the case with inorganic semiconductor. Rather, these are quasi-particles such as solitons, polarons, and bipolarons whose movement along the chains makes the polymeric materials conducting, and the formation of these quasi-particles is energetically possible process.
Conduction. In the chains of organic polymers, it may be energetically favorable to localize the charge around the chain, which is associated with a local distortion of the lattice. The process which causes the presence of local electronic states in the energy gap of the polymer due to local upward and downward shift of the valence and conduction band analogues, which is called as HOMO, means highest occupied molecular orbital, and LUMO means lowest unoccupied molecular orbital, respectively, which is clear from the figure below. Oxidation of the polymer chain may end up removing an electron from the chain, resulting in the reduction in the ionization energy, say by an amount delta E. In this chain, the energy is larger than the energy that is required for local distortion of the lattice, that is E distortion, then the formation of a localized charge is a favorable process in comparison to the band processes. This process is also associated with a strong coupling between the lattice and the electrons. The difference between the two energies, that is delta E minus E distortion, is a measure of the binding energy of the polaron. The calculated polaron binding energies for various conjugated polymers are in the range 0.03 electron volt to 0.12 electron volt for the materials such as polyacetylenes, polyparaphenylene, and polypyrols. Upon polaron formation, the valence band remains full while conduction band is empty with no metallic character. This figure shows the schematic of the formation of a polaron, bipolaron, and soliton in organic polymers. Now, the explanation is as follows: that the removal of a second electron from the polymer chain, that is, dimerization results in the formation of a polaron or a bipolaron. That is, by removing an electron from already formed polaron, which is clear from the figure also. This process is also energetically stable despite the higher Coulombic repulsion between the two charges of the same sign confined to same location in the lattice, that is, to the same polaron. The Coulombic repulsion is also screened by the presence of dopants with opposite charges in the polymer chains. The binding energy of bipolarons is calculated to be larger than that of polarons. In polymeric materials such as trans-polyacetylene, which have degenerate ground state, the bipolarons can further lower their energy by dissociating into two spinless solitons forming at the mid-gap location. Now here the students can be noted that the bipolaron can also be called as dianion. It must be noted that the solitons do not form in the materials such as polypyrrole, polythiophenitic, which do not have a degenerate ground state. Doping. So students, here we will be discussing about the chemical doping. Let us start with a brief introduction. What is the need for the doping of polymers? Doping of polymers is a tremendously powerful tool to tailor their electrical behavior from being a metal into an insulator and is performed at much higher levels, that is 20 to 40% in conducting polymers than in semiconductors. For example, conductivity of polyacetylene changes by 7 orders of magnitude upon AsF5 doping. Chemical changes leading to the changes in the electrical behavior are achieved by doping the polymer either by chemical route or by electrochemical route as each repeat unit. That is, in a polymer, mer is a potential site for redox reaction or chemical reaction. When the polymer is doped with the ions of difference valence, it leads to the change in the electrochemical potential or the Fermi level of the polymer, either via a redox type reaction or an acid-base like reaction, whilst the electrical neutrality is achieved by counterions. The Fermi level moves in such a direction where there is higher density of electronic states. The charged species caused as a result of doping lead to the development of electrical conductivity, with these charge carrier moving along what is called as pi bonded highway. However, disordered structure of polymers limits the electrical mobility of the carriers. Doping in the conjugated polymers can be achieved by a number of methods. First is chemical, second is electrochemical, then photochemical or interfacial. So here we will be discussing about the chemical doping. Chemical doping is based on the principle of charge transfer, which utilizes the redox chemistry, that is either oxidation or reduction. Doping with the p-type dopant results in the oxidation via the removal of electrons, whilst n-type doping results in the reduction of the polymer by adding the electrons. Now these are the reactions that illustrates the two kinds of doping phenomenon. First we will discuss about the p-type doping. Doping of trans polyacetylene with an oxidizing agent such as iodine, leading to nearly 6 orders of magnitude increases its conductivity. So the following reaction corresponds to the p-type doping. Now next is the n-type doping. Doping of trans polyacetylene with electron donors such as sodium. This is governed by the following reaction. It is also been found that n-type and p-type doping also compensate each other. Now students, we will discuss the next type of doping, that is electrochemical doping. Although chemical doping is a straightforward and a simple way of doping the polymers, the control of the dopant amount can be difficult. While high doping yields good results, moderate levels are not so easy, and they are found to result in inhomogeneous doping. So, to circumvent this problem, Nigaret et al. Invented a process which is called as electrochemical doping. In electrochemical doping, a polymer is coated with the electrode and another electrode is kept in an electrolyte. For example, polymer electrode can be trans polyacetylene, which is coated with a positive electrode, and the other metal electrode is chosen as the negative electrode, and they both are immersed in an electrolyte, which is a solution of LiClO4 in propylene carbonate. Once the DC power is applied to this electrochemical system, the electrode attached to the polymer supplies redox charge to the polymer. At the same time, electrolyte serves as a medium for the transport of ions either in or out of the polymer to compensate the charge on the polymer. The extent of the reaction and hence doping levels are determined by the DC voltage applied between the electrodes, and hence it can be controlled quite easily. Also, the process is reversible so that one can achieve doping as well as undoping. Also, both N and P type of doping is feasible. Now, these are the reactions which represents the electrochemical doping mechanism. In the case of P-type doping, there is Li plus 1 Bf4 minus 1 in the solution form plus pi polymer gives lithium electrode plus pi polymer plus 1 Y Bf4 minus 1 Yn. And in the case of N-type doping, lithium electrode is added to the plus polymer, that is pi polymer N, gives us Li plus 1 Bf4 minus 1 in the solution plus Li plus 1 Y pi polymer minus 1 Y N.
Now we will discuss the various other doping methods. First doping method which we will be discussing is photodoping. If a polymer is irradiated with a light beam having energy higher than the band gap of the polymer, it can create the electron hole pair and consequently it creates the free carriers. So one can also view this process as the polymer undergoing local oxidation and reduction due to the absorption of the photon. So we can view this by the example using trans polyacetylene, which when irradiated gives the two oxidation or the oxidation and the reduction states of the polymer. So, however, once the radiation is stopped, the process of the carrier creation may cease, although the application of an electrical potential during light irradiation can lead to high conductivity. Also, photodoping, there is no role of counter ions and the change of the conductivity is not permanent. Next type of doping which we are going to discuss is the doping by the charge injection. Since conducting polymers are used in device applications, they are often in contact with the metal electrodes. For example, metallic contact can inject electrons and holes into the pi plus and the pi bands respectively. The hole injection into the pi band can be represented by the reaction, where in this case, while the polymer appears to be doped, there are no counter ions participated in the doping process. The polymer is again either oxidized or reduced depending on whether the electrons are added or removed. Next type of doping method is the non-redox doping. While redox doping causes a change in the number of carriers in the polymer backbone, the non-redox doping causes only a change in the energy levels without changing the carrier density. Polyaniline is a model system for such kind of studies. Polyaniline, upon reaction with protonic acids such as HCl, gets protonically doped by H plus ions, which leads to a change in the geometrical bond lengths. This leads to redistribution of charges as well as the spin and results in the creation of half-filled bands, resulting a state with higher conductivity close to that of metals. So, there is a change in the structure due to proton-induced spin unpairing, but there is no change in the number of electrons. So students, let us summarize what we have learned in this module. First, conducting polymers have emerged as a class of materials which generated substantial excitement due to some of their extraordinary properties and potential for various applications, in particular electronic devices such as displays, solar cells, and sensors. Second, the semiconductivity in polymers can be created by doping these polymers in a similar fashion as in the inorganic materials, but with different approaches. The next conclusion is the pi conjugated structure of polymer chains allows the creation of polarons, the charged species, which allows the hopping between the Mohr units, giving rise to conductivity. The conductivity can be tuned by the orders of magnitude depending on the material and dopants, as well as the method of doping, allowing one to tailor the material with greater ease. Thank you.